Okay, we're moving on with section 5.6, Newton's third law. And let's get to the PowerPoint. And this is Newton's third law. If two objects interact, the force F12 exerted by object 1 on object 2 is equal in magnitude and opposite in direction to the force F21 exerted by object 2 on object 1. So the force 1,2 is equal to minus the force 2,1. You've commonly heard this for every action, there is an equal and opposite reaction. That's the common rephrasing of the term. What it's saying, if two objects interact, one is exerting a force and the other is exerting an equal and opposite force. That's the easiest way to say it. Let's look at this. Let's get the notation down. The FAB means the force exerted by A on B. So F12, 1 is this little blue ball, and 2 is the larger tan ball. So for F12, 1 exerts on 2. The action of the force 2,1 is the reaction force, or vice versa. If you're looking at F12, then F21 is the reaction force. Note that the action-reaction forces act on different objects. It must be of the same type. In other words, you can't have one force be a gravitational and the other be an electromagnetic. These are both the same type of force. In this case, it's not specified. We're assuming that this is gravitational force of one object on the other, but it could just as easily be an electromagnetic force. If you have a negative charge attracting a positive charge, then you have the positive charge attracting the negative charge. And if we're talking gravitational, then you have the object 1 having a gravitational force against object 2. Well, object 2 has the same but opposite force on object 1. A force acting on a freely falling projectile is equal to the gravitational force exerted by Earth on the projectile, Fg, and it's equal to the FEP. That is, the gravitational force is equal to the FEP, the Earth on the projectile, and the magnitude of this force is mg. The reaction to this force is the gravitational force exerted by the projectile on the Earth. FPE equals minus FEP. Let's see, there's an equation. There you go. F gravitational is equal to FEP. FPE, the particle on the Earth, is equal to minus FEP. It is there. And the acceleration, because the Earth is so massive, the acceleration is very, very small, but the force is there. Reaction force FPE must accelerate Earth toward the projectile, just as action force EP accelerates the projectile toward the Earth. Earth has such large mass that the acceleration is negligibly small. Okay, let's look at this computer monitor at rest on the table. Earlier I was talking about my laptop on this desk, but now we're looking at the computer monitor at rest on a table, as in figure A. That's the left-hand side. The gravitational force on the monitor is Fg. It equals to F, the Earth, attracting the mass of the monitor. The reaction force is Fme equals minus Fem exerted by the monitor on the Earth. The monitor does not accelerate, it's held up by the table. The table exerts on the monitor an upward force, N, the normal force, and it's FTM, the table on the monitor. Normal means perpendicular in this case, not if you have a surface, the normal to the surface is perpendicular to the surface. That's what normal means, not normal like we're used to using. He's a normal kind of guy, not that kind of normal. In general, whenever an object is in contact with the surface exerts the normal force on the object. The normal force on the monitor can have any value needed up to the breaking point of the table. Because the monitor has zero acceleration, Newton's second law says that the sum of the forces is the normal force plus the weight, mg, it equals to 0. So it's n in the j direction minus mg in the j direction equals 0. So n equals mg. The normal force balances the gravitational force on the monitor. So the net force on the monitor equals to 0. The reaction force to N equals the force exerted by the monitor downward on the table. So F monitor to table equals minus F table to monitor equals to minus N. Forces acting on the monitor are Fg and N, as shown in figure B. Fme and Fmt exerted on the objects other than the monitor. Okay. Let's learn about free body diagrams. Figure A shows many of the forces in this situation. Those acting on the monitor, and one acting on the table, and one acting on the earth. Okay, figure B, only the force is acting in one of the objects is the force diagram on the monitor. Figure C is the free body diagram. The particle is a model used by representing an object as a dot and showing forces that act on the object applied to the dot. The free body diagram helps isolate only forces on the object and eliminates other forces from our analysis. Okay, that's a free body diagram, and it will help you in the future to learn how to draw free body diagrams as you to solve problems. Let's see. If a fly collides with the windshield of a fast-moving bus, which experiences an impact force with a greater magnitude, the fly or the bus? The same force is experienced by both, believe it or not. Now, let's get to the important question. If a fly collides with the windshield of a fast-moving bus, which experiences an impact force with larger magnitude? I'm sorry, that was the same one. If a fly collides with the windshield of a fast-moving bus, which experiences the greater acceleration? The fly, the bus, or the same acceleration is experienced by both. Remember, force is equal to mass times acceleration. So the force is the same on each, but since the mass of the bus is so much greater, the acceleration is, you remember the F1 over F2 is equal to, there was I'm sorry, it was, I think, mass 1 over mass 2. The acceleration is 2 over 1. The acceleration is greater for the fly. The acceleration is greater for the fly because the mass of the bus is so large. Okay. Because the fly has such a small mass, Newton's second law tells us that it undergoes a very large acceleration. The large mass of the bus means that it more effectively resists any change in its motion. It exhibits a small acceleration. It has greater inertia. Okay. Let's look at another example, a conceptual example. A large man and a small boy stand facing each other on frictionless ice. They put their hands together and push against each other so that they move apart. Who moves away with a higher speed? Who moves away with a higher speed? Okay, well, according to Newton's third law, the force exerted by the man on the boy and the force exerted by the boy on the man are a third law pair of forces. So they must be equal in magnitude. A bathroom scale placed between their hands would reach the same regardless of which way it faced, towards the man or towards the boy. Therefore, the boy having the smaller mass experiences the greater acceleration. Both individuals accelerate for the same amount of time, but the greater acceleration of the boy over this time interval results in his moving away from the interaction with the higher speed. So the boy moves away with the higher speed. Okay. Who moves farther? Oh, let me. Oh, I gave away the answer. Who moves farther while their hands are in contact? Well, you already saw the answer unless you blinked. Because the boy has the greater acceleration and therefore the greater average velocity, he moves further than the man during the time interval during which their hands are in contact. So the boy, the man has a greater mass, so he has more inertia. This ends our discussion of Newton's third law. We will next discuss analysis models using Newton's Newton's third law. I almost said second law. It's a long section. The next section is a long section. I'll probably break it up into 3 sections, just to not have so long. So yeah, that's it.